taking a seat, perhaps? Yeah, I'm sitting.
Oh, say that again. I'll play. We're going to build up. We're going to build up.
All right, so I guess we'll just get started. We are Team Deep Vision, and we worked on an object identification system, which uses an FPGA computer vision system. So the outline of our project. The purpose of this project is to create an object identification system which can be utilized for airport security to identify hazardous objects being brought onto a plane. The software will run on an FPGA board that allows for real-time object identification due to the increased performance versus other boards. The neural network will be trained using a machine learning algorithm. Specifically, we will be implementing the yellow V3 machine learning algorithm. And objects will be transported using a conveyor belt, which we have designed and developed. The belt will have a camera mounted onto it, which sends live video stream to the FPGA board. So, team member introduction. I am Alvaro Daniel Cerqueda. I am team leader, software lead. Then we have John Healy. He is the hardware lead. And then Geneva Royer, who has been leading the FPGA research and data collection research.
Our project motivation, the minimum wait time to arrive at the airport is approximately 2 hours. So we developed the FPGA-based computer vision system to speed up the time to load the wait time to arrive at the airport. And our project is, our FPGA system is inline type. Unlike the other FPGA, we connected the camera, the microcontroller, the PC, and the conveyor belt together instead of a separate entity. Our goal is to create an image detection system. So our criteria, there's 4 criteria: cost, feasibility, high resolution imagery, and efficiency. So there were 3 alternatives to do the co-processing vision system, the inline vision system, and the GPU system. We picked the inline vision because it takes up all 4 of the criteria. So our key components is the YOLO version 3 software. It provides the algorithm for the object detection system. Also, it's compatible to the microcontroller. Our microcontroller is AVNet Ultra 96. It's a combination of hardware and software because they use the software E-Links, which implements the pin assignments for the microcontroller. Then there's the camera, which provides the imagery that YOLO is going to process. Finally, the conveyor belt, which brings the objects towards the camera. So on top, it's the engineering requirements. And on the side, that's the marketing the marketing components. So our main interest is the high resolution, because without the high resolution, we would not be able to implement the object detection. So we put them in 3 categories: high quality imagery, easy to use, and efficient operating system. So for the high quality imagery, we focus on the resolution, the color detection, and noise filter. For easy to use, we focus on the signal and the inputs and outputs. Finally, for the efficient system, we focus on the memory storage, minimum microcontrollers, and official power usage.
All right, so as system description, first off, our hardware will be the conveyor belt, which we have Dr. Wang, the group from last year, built it, and he was nice enough to let us use it for our project. Our camera will use onboard firmware to take a picture of the item that we will be scanning and feed it to the FPGA microcontroller. This will use object tracking and a classification program that will be coded in Python to determine whether or not the item is safe, and that will be output onto a computer. We will use Xilinx, which is a software design tool, which will allow us to speak between the microcontroller and the computer.
So related theory, for the machine learning algorithm and the neural network itself, that's where most of the mathematics will be taking place. So for machine learning, the cost function is utilized to adjust the weights of the neural network being trained based on the difference of the expected output and the calculated output. You can see the equation itself there. It's used to hone in on what the weights should be based on the error on each iteration. And then neural networks utilize activation functions to determine which nodes must be processed, or which nodes need to process the input to generate the correct output. So the yellow V3 algorithm specifically utilizes the rectified linear unit activation function, and you can see a graph of the activation function on the slide.
All right, so our behavioral module, we have 3 inputs and 1 output. Our inputs will be a picture, which again, we will have a camera mounted. It will snap an image of whatever item we will want it to scan. And this picture will be fed into the FPGA microcontroller, which has a machine learning algorithm built onto it. Then this algorithm will use an image database, which again we will upload onto the FPGA to determine whether or not the item is safe. And then if image enhancement is needed, that will be used to just ensure that the item or the image is legible and visible. And then our output will be a tracked object data. This will analyze the input image and send this information to a user interface. And then the functionality, we can see here, the item will travel down the conveyor belt, an image will be taken and processed. It will be sent to the FPGA microcontroller, which will use this machine learning algorithm to determine if the item is hazardous or not. This will be relayed to a user interface, and then a worker will do what they will with the item. Our functional decomposition. Our module has 2 inputs and an output. So we will have an AC/DC power supply, and our camera will be our visible light input signal. So the camera will take a picture. It will convert the picture into a digital number, which will then be processed and by the microcontroller, and that will determine again whether or not the item is safe. And then our functional decomposition, level 1, it is broken down into sensory and computing components. Our sensory component is the USB camera that we will be using. The camera requires 5 volts of DC power. So again, this is just reiterating, it will take the picture, convert the picture to a digital number. This number will then be fed to our computing component, which is the FPGA microcontroller. Then it will use the machine learning algorithm that we will code and figure out whether or not the item is hazardous, and then output that info to a user interface. And then this is just a brief diagram explaining what will be going on.
Okay, so here we have the demonstration video of the conveyor belt, which is functional, and it also has the arm, which has the camera mounted on it. That's the work that we did on top of the conveyor belt, which was provided.
Yeah, so as you can see, the conveyor belt is composed of, those are zinc-plated iron bars. There's some PVC tubing down the middle of it, and what is rotating around is a bicycle tube that has been cut and glued together. Down here, this is a 12-volt motor that will be running everything. It is connected to a PVC pipe that will allow everything to rotate. In order to avoid slippage, there's grip tape around some of the tubing, and then the camera mount is just under 2 feet above the machine, so that it will give the camera an optimal diameter in which to take the picture. And then, yeah, this is what I just...
All right, so software design and implementations. So the reason why we decided to use the yellow V3 algorithm, there were 3 main reasons. One is that it is an incredibly well-documented algorithm. We were able to find a lot of projects that implemented it, and instructional videos and just tutorials that kind of explain the different aspects and components that you need to use to get it functional. Another reason is that the algorithm is compatible with Ultra 96 FPGA board. It's actually listed as a compatible algorithm on their website for the board, which also leads into our original one of a lot of documentation with the algorithm. And the third reason was that there are pre-made classes which can be imported. So a pre-made class for the algorithm is a shape that the algorithm has pre-programmed for different objects. And that increases your ability to identify different hazards and different objects with ease by making it simpler to import different hazardous objects and their images and not need to require such a vast database of pictures. The database that we were using for images has, it's the Google Open Images V4 dataset, and we found only 770 images for the mock algorithm that we were developing. So that's not very much data, which is usually, you would prefer to have more data for a machine learning algorithm. That's why we thought the algorithm, the yellow V3 algorithm would be useful, because these classes help us make that enough data and still get high confidence despite the lack of vast numbers of images. So, how to implement the yellow V3 algorithm. First, you install the algorithm. You need to download a data set and split that data set into training sets and a testing set. We fetched that data using Google's Open Images V4 dataset. We used a script which automatically downloaded them. Then we installed Darknet and configuration, and we configured the code for our specific needs. Darknet is a deep learning framework utilized to develop and build neural networks. It allowed us to kind of cut down our time and the amount of effort that we had to put in by importing somebody else's model and then developing it with our own weights, which we processed and generated with our yellow algorithm. So then step 4 was to download a pre-trained model just to improve the training rate. So that was a pre-trained model for object identification. This is common practice with machine learning and computer vision systems. Then step 5 was to set the yellow V3 configuration parameters to our specific needs. These parameters are very nuanced and detailed and are fully explained in our report. And then step 6 was to train the yellow V3 algorithm, and step 7, also, I should say that step 6, that involves running a command and a Linux system where you take the algorithm and then you feed it the data, and it kind of runs over time. For us, we had a virtual machine running it, so it took an extensive amount of time, a few hours. And then it generates a output file of weights. And then you test the yellow V3 algorithm with that weight file that is generated while training it. So here's a software demonstration. There's a list of images that we have for testing. None of these images, the locations of these images, none of these images were used for the actual training of the algorithm. So it's not specifically trained for these images. Then we run the command in our VirtualBox. First, I brought up the original image of snowmen. I'll explain why we use snowmen instead of knives or hazardous objects in a second. But there's our snowmen, and we're going to be identifying snowmen when we run it through the command. So the algorithm will generate an output file, and then we will open that output file. And once we open it, we'll see that all the snowmen have been identified. So the reason why we started off with snowmen, rather than the hazardous objects that you would want to avoid bringing into an airport, is because we found a very detailed, very extensive tutorial on how to actually get the algorithm up and running using snowmen. And thanks to the fact that the algorithm has pre-built classes, and we fully understand the whole process that the tutorial is explaining, we think we'll have an easy time transferring our current algorithm and redeveloping it, recompiling it with different images and different classes to fit the hazardous objects that we will be using for our final product. This was more of a trial to make sure that we fully understood it before we try to implement it on our own, where there would be no step-for-step instructions. So, iterations that were performed to develop the optimal software design. We had an issue where we were trying to use a virtual machine to compile it, to generate the weights that I mentioned before. However, our virtual machine did not have enough allocated memory. We only had 2 gigabytes of RAM. So our second iteration, we increased that 2 gigabytes to 4 gigabytes. And once we did that, we were able to compile the program successfully. With regards to hardware, we had everything functional actually on the first attempt, so we didn't have multiple iterations for our hardware components.
All right, so this is a test, the unit test that we performed on our hardware component. It is a white box test. So the conveyor belt passed 3 out of the 5 tests that I performed. All it really consisted of was me hooking up the motor to a 12-volt battery and seeing whether or not the motor ran. So what went wrong in the 2 tests that failed was the battery that I was using had died and needed to be recharged. So once I did that, I hooked it right back up to the motor and everything ran smoothly.
Yeah, since the main issue was just the battery, not the actual hardware, and we won't be using that battery, we didn't decide to mention that in our iterations performed to develop an optimal design. It just didn't seem pertinent to our final project.
For the software testing, first we try to use OpenCV on a Visual Studio environment. I tested it 2 times. I tried to use the tutorial that was on Learn OpenCV. Unfortunately, it didn't work. The first attempt didn't work because I used a newer version of the OpenCV and a newer version of Visual Studio. The newer version of Visual Studio is not compatible with the software they were using, so it did not work. The second time, as a result from the first one, the computer didn't want to install that method again. So I used a YouTube tutorial to download it, but by the time I finished implementing OpenCV into Visual Studio, I already did the Linux environment and successfully tested it, so we decided to go with the Linux environment.
Another reason why we decided to go with the Linux environment is the FPGA board itself runs on Linux, so we figured it would be easier to kind of port over our work onto the FPGA board and finish it there if we use the Linux environment. So another software test. This was just testing the images, the image identification of snowmen. This was a white box test using 5 images. 4 of the 5 tests passed without any hiccups. The one failure was more of a bug, not so much a failure, where there were actually 2 boxes around a single snowman. So this was unexpected and something that we could definitely look for a way to improve and resolve. However, it was still identified. The object had no issue being spotted by the algorithm. And then our second software test for the Linux version was just a video test. We actually were a bit ahead of schedule. We were expecting to only be able to process images. However, we managed to get a video test that would identify a snowman in a video. We only performed 1 video test with only 1 video due to the computational intensity of performing this on a virtual machine. We believe we'll be able to perform it much quicker on the FPGA board, so we will return to this type of test once it's uploaded onto the FPGA board. However, this test was passed. The board was able to identify the video, or the virtual machine was able to identify the snowman in the video without a hiccup. So our go, not go milestone work. The hardware milestone that we were aiming for was to have a functional conveyor belt. which could transport items to the camera. Dr. Wang provided this component towards the end of the semester, which gave us about 2 weeks to make any modifications prior to the demonstration. So our modification that we went with was the camera mount, which is added for the Milestone. We intend to develop the conveyor belt further and to make more modification and enhancements. Once we have the software on the FPGA board, we'll be able to send output signals, which are controlled by the software, and then we can add things like LEDs to highlight if an object has been spotted, or even an arm that could slide the hazardous object off the conveyor belt. We have room for growth there. The software milestone was to have a neural network which could accurately identify images of snowmen. The goal was achieved. We were actually, like I said, ahead of schedule. We were able to identify snowmen in videos by the time of the milestone demonstration. So our project schedule for winter break, there are 3 main branches. There's going to be the software, bringing the software to the FPGA board itself. That's the first 2. I'll be handling that. The research of how to process inputs and outputs using an FPGA board will be handled by Geneva and John. And then the 3rd branch is hardware. The hardware is designed, it's the second augmentation that we'll be making to the conveyor belt. We'll be adding a piece to hold the FPGA board within reach of the camera, and we'll also need to make it designed so that we could plug it into a monitor that the operator would be able to use. So there's a bit of design and development that has to be done there. Our planned work for next semester is to connect that camera to the FPGA board and run the live identification software program on the FPGA board. Once we have that functional, we'll be able to make additions, like I mentioned, to the conveyor belt system. Another addition that we may add is stopping the belt automatically if an object is detected, or even having the belt just fully controlled by the operator. And last, if all that is functional, we'll be able to add more items to our list of hazards. At the moment, we're intending to focus on just getting one item, such as a knife. However, in the future, if we get this functional, we'll be able to add multiple items and retrain our neural network to identify those different items.
All right, so this is our cost analysis. It is a list of all the materials that we had bought. Things get a little hairy here. Everything that's yellow and crossed out, I had ordered all the parts previously, and then Dr. Wang had lent us the conveyor belt from last year to use, so I had to return most of the parts. That's everything you see in yellow. Everything in black I kept and utilized in building the camera mount and adding it onto the belt itself. So our cost is around $110 right now, which leaves us with $240, give or take, to spend if needed. And
that gives us plenty of budget to add those components as mentioned before, such as LEDs or that arm that could separate the objects.
So our main code and standards and constraints is the New York State's right-of-way and the International Radiation Protection Association of 1990. So the system itself should not exceed the maximum electric field of 5 kilovolts per meter, and the highest magnetic field should be 1 G, which is approximately 0.1 millatesla. Mainly, this is because this is supposed to be for the general public. General public should not have that emission for a 24-hour interval, and since the airport is 24 hours, this is the reason why we constrain it to the magnetic field and electric field. Also, the camera should be able to detect objects within the dimension of 9-inch time by 14-inch by 22-inch, because that is the maximum size for a carry-on. So overall, our Capstone project is to make an FPGA-based computer vision system. So first, that can detect objects within a 9 19 by 14 by 22 inches cubed. And once it detects the objects, it will emit the LED lights, and it will disable the Bluetooth, because you want to disable the Bluetooth to avoid encryption and hacking. So the project will positively impact the society because it will lower the wait time for the airport, domestically and internationally. Also, it will lower the cost for security costs, because the majority of the money for security is based on the TSA security technology. So far the cost of our device is $109.62, but a republished CT could cost $65,000. So the main ethic issue is mainly the ethics of the TSA security workers, because they're in charge of reporting and observing all they're responsible to see if there's any breach of security. Also they're in charge of training their juniors how to use the technology as well. And we recommend that the TSA workers train them properly, take the time to train them properly, and make sure that they maintain their ethic. Also, having a high quality camera will also help the efficiency of the device.
So conclusions and future work. The project so far is on schedule to be complete by April. All group members have been able to complete their modules independently, which is vital considering our group size of 3. If we want to stay on track, we'll all have to be able to kind of handle everything individually and call people in for assistance, but not fully work together on aspects. Otherwise, we just won't be able to cover enough ground in time for our final presentation in April or May. And if all assigned winter break tasks are completed when expected, next semester will primarily focus on the integration of different modules and features within the FPGA board. Here are our references. Any questions? Great, thank you.